There. In this video, we will look at Taylor's inequality. We are given a function f of x and a Taylor polynomial t subscript n of x at the point A. We are interested in the approximation error of the approximation. That is, the absolute value of the difference between f of x and t subscript n of x. We will denote this error by r subscript n of x. So it is the difference between the real function value and the value of the Taylor polynomial at the point x. Taylor's inequality is a theorem that makes a statement about this approximation error. It does not tell us what the error is, because then we would know the actual value and there would be no need for an approximation. All we can hope for is an upper bound for this approximation error. In practice, this is sufficient for most purposes. The theorem is displayed on the screen. It is a slightly technical result. So let's see what it really says. First of all, we need an interval d that contains the point A. In practice, we are given a point A, and we have to choose a convenient interval d containing the point A. The second ingredient is a positive number m. This number m denotes a convenient upper bound for the absolute value of the n plus 1th derivative of the function f on the interval d. Finding such an upper bound is usually the tricky part in applications. Suppose we have found such a positive upper bound m. Then the theorem states that for all points x in the interval d, the approximation error r subscript n of x is smaller or equal to m times the absolute value of x minus a to the power n plus 1 divided by n plus 1 factorial. The upper bound gets often larger if the point x is further away from the point A, as the x minus a term indicates. Note also that higher order Taylor polynomials give a better approximation, as shown in the n plus 1 factorial term, making the upper bound smaller for higher n. The best way to get a feeling for this theorem is to look at an explicit example. Let f of x be the exponential function e to the x and a is 0. The Taylor polynomial t subscript n of f was determined in the previous video. Let us recall fast how this was done. To find the formula for t subscript n, we need to determine the higher order derivatives of f of x and evaluate them in a as 0. Of course, f of 0 is equal to 1. Since the derivative of f of x equals f of x itself, it follows that f prime of 0 also equals 1. Continuing this, we see that evaluating the k derivative of f in 0 equals 1 for all k. Because of this, the nth order Taylor polynomial is equal to 1 plus x squared over 2 factorial plus up to x to the power n over n factorial. For example, for n is 5, this is equal to the explicit polynomial on the screen. Since e is f of 1, it is natural to approximate the Euler number e by t subscript 5 of 1. If we plug in x is 1 in t subscript 5, then we obtain the value you see on the screen. What is then an upper bound for the approximation error? Up to how many decimals is the approximation correct? To apply Taylor's inequality, we need to choose an interval d that contains the point a is 0 and the point 1. the most economical choice would be the interval from 0 to 1. To apply Taylor's inequality, we need the number m. For this, we need the absolute value of the sixth derivative of the function f of x, which is equal to e to the x. Since e to the x is an increasing function on the interval d, it achieves its maximum at x is 1, and this is equal to the number e. So we could take as upper bound the number e itself. But now we have a problem, because we are trying to approximate the number e itself. So e itself is not a convenient upper bound. What can we do? The idea is to take a less efficient upper bound, but one that is more convenient to work with. We will take as upper bound m is 3. Then m is still an upper bound and an easy number to work with. In this context, Taylor's inequality tells us that the approximation error for any number x in the interval 0, 1 is bounded by 3 times the absolute value of x to the power 6 divided by 6 factorial. Simplifying this gives x to the power 6 divided by 240. If we plug in x is 1, then we see that the approximation error in x is 1 is bounded by 1 over 240, which is approximately equal to 0.0042. So the approximation t subscript 5 of 1 is at least correct up to 2 places of decimals. To get an even better approximation, one can use Taylor polynomials of a sufficiently high order. This is precisely the way a scientific calculator actually calculates e to the x for any x. We finish this video with the exercise on the screen. What do we need to take for n if we want to approximate the number e up to at least 10 decimals?